Let's build a k-means clustering model in Python to help you better understand how it works. Today, we'll be building a full machine learning pipeline to cluster your data, and we'll be using a model called k-means++. Put quickly, k-means++ is just a smarter version of the basic k-means because it takes a more careful approach to choosing the initial centroids. So let's open up our environment and get coding. As always, we start by importing all the necessary libraries, and today all we'll need is NumPy for math and Matplotlib to make a pretty cool visualization later on. Now we're starting off with a bang because right off the bat we're defining a function called k-means++ that is designed to take in our dataset and cluster it. The dataset here is called X, and it is assumed to be one table of numbers. Each row is a point and each column is a feature. Parameters for this function are the datasets, how many clusters k we want, the maximum iterations or revisions we want our model to go through, and random state is just a seed planted for randomness. Inside this block, we simply report how many points and features the dataset has and set up a random number generator. Essentially, we're just preparing that information we need about the dataset to make controlled choices later. Here is where we prepare the storage for all of our centroids. Because a centroid will go on to later represent the center of each cluster, we need k number of rows and as many columns as there are features. This is like reserving k number of slots in the code's memory so the model can store them as it discovers the centers. The first centroid is chosen by picking one data point at random and declaring that as the first center. And this first choice really has no special structure, it just anchors the process so we can get going. Now here is where we're going to implement the core idea of k-means++ initialization. After the very first centroid is chosen, we want all of the remaining centroids to be spread out across our dataset, not all bunched up in one region. And to do that, we measure for each data point how far it is from its closest cluster center. Points that already sit close to a center will have a smaller value, and points that are farther away will have a larger value. And by the end of this block, we have a pretty good understanding of where all our data points sit in comparison to the one cluster centroid we have so far. Now we convert those square distances from the centroids into probabilities. Each point gets a probability that is proportional to how far it is from its nearest existing center. This means that points that are in regions that are not yet represented by a cluster center have a very high chance of being picked, and the points that are already close to a centroid have a lower chance. We then randomly select the next centroid according to these probabilities and store it. We repeat this for however many centers we want to have, and the result is k initial centers that are deliberately spread out across the dataset. This usually leads to faster convergence and better final clusters than using the basic k-means model would give us. This block right here begins the main k-means loop, and the first part of it is called the assignment phase. Now that we have our centroids, we want each data point to decide which cluster it belongs to. To do that, for every data point, we find how far it is from all the clusters using squared Euclidean distance. Find which centroid is closest to the data point and give it that corresponding cluster label. And after this step, every point has its own temporary cluster ID. Now we're moving on to the update phase, and this is the second part of the main loop. With the current labels fixed, we want to move each centroid to better represent the current members of its cluster. For each cluster index C, we gather all the points that are currently assigned to that cluster. Then for each cluster, we add up all of the points feature by feature and take their average. And this feature-wise average is now the new location for the centroid of that cluster. And now after this block, we officially have new locations for all of our clusters. This loop of the assignment phase and the update phase continues on and on and on until the algorithm has stabilized, which we're defining in this block. Essentially, we want to stop revising the clusters when nothing much is changing from iteration to iteration. So if each data point is picking the same cluster center every time and the centroids aren't changing a lot, then we say the algorithm has converged. And we'll check if the algorithm has converged for every single pass or until the max number of iterations has been hit. At the end, we return two things, the final centroids and their labels. And here are the results we're looking at for this specific model. And now that we have the full pipeline defined, this block here is where we're actually defining our data. The idea for this model specifically is to make a very simple synthetic dataset that clearly has three groups. Each blob is a bunch of points sampled from a normal distribution centered at a particular location on the XY plane with some spread in there so that the points still look somewhat realistic. Then we stack these three groups on top of each other into a single array X, which has 300 points and 2 features. And this X is the dataset that will be fed into the k-means++ function we defined before. Now here is where we actually run the clustering on the synthetic data. Here's an elbow graph I plotted really quickly to help us determine how many groups we want in our dataset, and it looks like the optimal number of clusters here is 3. So we tell the model that k equals 3 to create 3 different blobs. Then we pass all of these parameters into the k-means++ function, which will cluster the data for us. And here is the complete clustering for this model and this dataset. It looks like our model did exactly what it was supposed to do and converged quite well. This is a very simple and obvious dataset to cluster, but this is one of the most important models data scientists use for real-world data as well. And that is a fully functioning k-means++ clustering model coded for you in Python right in front of your eyes. Full code is linked right here, so if you learned something from this video, then don't forget to save it and follow for more.